So one common application of simple differential equations is population models. So suppose we've got a bunch of bacteria in a petri dish here, and every time that you look under the microscope, you notice that there's a certain number of these guys that are engaged in binary fission, so reproduction, right? And maybe it's like a tenth of them. Then what does that mean? That means at the next time step, there's going to be an addition to the current population equal to 1/10 of the present size of the population. So this means that the time rate of change of the population of your critter is going to be 1/10 the amount of the current population. So P of t here is going to be our dependent variable, and it's going to indicate the population in time t in the number of organisms that we're interested in. And we're talking biology right now, but it actually applies equally well to things like money in a bank account and radioactive decay as well. So in general, one would write that p prime looks like some number times the current population p, and here k is some positive growth constant. Okay, we will see later that the solution to this differential equation is that p looks like some constant times e to the kt. And so because of that, it's referred to as an exponential growth model, or sometimes a Malthusian growth model. And this constant p right here, this is the amount of population that you start with. So the initial population, or more generally, we refer to the value of the dependent variable at time 0 as an initial condition, or IC for short. And then an initial value problem would be the differential equation p prime equals kp together with a specified initial condition. So maybe say 1,000. And then in this case, we would see that the particular solution is 1,000 e to the kt. So just to define those terms there, this one that we had back here, this would be called a general solution. And then when we add into that the initial condition, and we have the following specific case, this would be called a particular solution. Okay, so now if I graph the solution curves for this, so suppose we look at, here's increasing time, and here's my population. If I choose a particular p naught initial condition like this, then the population is going to grow without bound like that. I have this exponential curve coming from the fact that our solution is an exponential function. And so I'm just going to get similar copies of this curve depending on what initial condition I choose. So there's an immediate issue with this kind of a growth model, and that is that all the solutions increase to infinity without bound, which is completely unrealistic because in any actual population, there's going to be constraints. So we need to incorporate something called the carrying capacity if there's going to be any sort of realism to this model. And so the carrying capacity, will denote it by m, and that's going to be for the max population. And how do we incorporate this into our model? Well, if we go back to the original equation, what was it trying to record? It was saying that the rate of population change is proportional to the current population size. And so if we write this in terms of symbols, then what we have is the following. The rate of population change, that's in blue, is proportional to, that's equals a constant times, the current population, that's P. So there's our differential equation, right? Now, if we want to have something that's dependent on how much space is left in the system, then let's see. So M is the maximum population. So how much space is left? Well, M minus P then is going to be the amount of remaining space. And so, while it's not possible for a population to grow above M, a population can start with initially above M, and then what would happen is we would just see the population die off. So let's see. So how do I incorporate this, let's say, orange condition into the equation? Well, I'm just going to make it also proportional to the amount of remaining space. All right, so now let's look at the resulting solution curves. We're going to have P on the vertical, T on the horizontal, and let's say we've got our max population here is going to be this line right here. So here's our M. Then the solution curves are going to grow exponentially until they get close to M, and then they're going to asymptotically approach M. And so that's true no matter where you begin. So you get populations that look like this. And like I said, if you start with initial condition above M, then it's going to exponentially decay down to M, something like that. And this is called the logistic growth model. And so we'll see in the upcoming sections how to solve and find the solutions for each of these.